welcome to today's webinar, Build IoT Backends with AWS IoT and AWS Lambda. Our presenter today is Vyom Nagrani. Vyom is a Senior Product Manager for AWS Lambda. Today with us, we also have Ajay Nair, Senior Product Manager for AWS Lambda, and Olawell, Solutions Architect, AWS. Ajay and Olawell will engage with you and answer your questions throughout today's presentation. So Vyom, welcome, and I'll pass the floor to you.
Thanks, Bowen. Hello, everyone, and welcome to the Best Practices for Building IoT Backends with AWS IoT and AWS Lambda webinar. My name is Vyom Nagrani. I am the Product Manager for AWS Lambda, and I'll be your presenter for today. I have with me here today Ajay, also Product Manager for AWS Lambda, and Olawale, Solutions Architect with a focus on IoT, to help address your questions over chat throughout the webinar. If time permits, we'll also do an open Q&A at the end of the webinar where I will address commonly asked questions. Quick note on the Q&A, we welcome all types of questions during this webinar, but the Q&A panel will not be able to address roadmap questions or timelines of upcoming features on both of these services. So we do apologize for that in advance. The intention here is to help you understand these two services in depth, so we have to give priority to addressing your technical questions around building IoT backends on AWS. Preempting a common question which we expect, when is the Lambda VPC feature coming? I would like to answer that one up front. We are almost there. This feature is coming real soon now. With that said, let's jump into this webinar. We'll be breaking the webinar into 3 parts today. First, I will start off by a brief overview of what both of these services are and how they can be a very useful tool for building IoT backends. Next, given IoT is a new service by AWS, we will go a bit deeper into the features and functionality of that service and how that would be relevant for building backend applications. Lastly, we'll go through a quick demo of how to set up a IoT backend using these two services on the AWS console. Towards the end, we will also walk through an alternative reference architecture and code templates for how to set up a production-grade IoT backend application on AWS. So let's start with the AWS IoT service. AWS IoT is a managed cloud application platform that lets connected devices easily and securely interact with cloud applications and other devices on AWS. AWS IoT can support billions of devices and trillions of messages, and you can process and route these messages to AWS endpoints and to other devices reliably and securely. With AWS IoT, your applications can keep track of and communicate with all of your devices all the time, even when they are not connected or have limited internet connectivity. AWS IoT makes it easy to use services like AWS Lambda, Kinesis, Amazon S3, Amazon Machine Learning, Amazon DynamoDB, etc. to build IoT applications that gather, process, analyze, or even act on data generated by these connected devices without you having to manage any sort of infrastructure. The AWS IoT service offers a common set of capabilities that you will likely need no matter what IoT scenario you are targeting. This may range from connecting with the devices, to managing the communication protocol and network, to managing device security, to collection of data from all of these services for further processing, to the real intelligence behind your development. With AWS IoT offers these capabilities to you so that you can focus on what differentiates your connected devices, your application, and the IoT services for your end customers. The primary functionality of this service is the connectivity between the devices and the AWS cloud. With AWS IoT, you can communicate with these connected devices securely with low latency and low overhead. The communication can scale to as many devices as you want, since the AWS IoT service supports standard communication protocols such as HTTP and MQTT. And communication is also secured using TLS. Secondly, the AWS IoT enables you to start processing the data sent from these connected devices. With AWS IoT, you can continuously ingest, filter, transform, route, or even selectively forward the data stream from connected devices. You can take actions based on the data and then route it to further processing and analytics. Finally, a big part of AWS IoT is to make it really easy to create and also accelerate application interaction with these connected devices. So it serves as an easy user interface for these applications running in the cloud or on mobile devices to access the data sent from these connected devices and send the data back to these connected devices in form of commands. So let's quickly talk of the benefits or why it's a good tool for building IoT backends. So what we'll see is that connected devices such as sensors, actuators, embedded devices, smart appliances, wearable devices, all of these connect to AWS IoT over HTTPS or secure MQTT. Included in AWS IoT is a device gateway that allows secure, low latency, low overhead, and bidirectional communication between these connected devices and the cloud or your mobile application. And we'll talk of this message gateway in a bit more depth shortly. The second is that communication with AWS IoT is secure. So all services require all of its clients, such as connected devices, servers, mobile applications, or even human interfaces, to use strong authentication. And with AWS IoT, you can get authentication mechanisms such as X.509 certificates, SigWi4 through AWS IAM credentials, or even third-party authentication via AWS Cognito. And all the communication that you do between the devices and the cloud is encrypted. It also offers a fine-grained authorization to isolate and secure communications along these authenticated clients. The third one is that the gateway supports a pub-sub messaging pattern, which enables scalable, low-latency, low-overhead communication to multiple endpoints. It's particularly useful for IoT scenarios where there are billions of devices and all of them are expected to communicate frequently and with minimal delay. The pub-sub involves client publishing messages or logical communication channels called topics, and the client subscribe to these topics to receive the messages. The gateway enables the communication between these publishers and the subscribers. And traditionally, organizations have had to provision, operate, scale, maintain, and spend a lot of effort in running these on servers as device gateways to take advantage of the pub-sub mechanism. But the AWS IoT has eliminated this barrier by providing a gateway with pub-sub right out of the box. The last one is that the AWS IoT service also contains a rules engine, which enables continuous processing of data sent by these connected devices, where you can configure rules to filter and transform the incoming data. You can also configure rules to route the data to other AWS services. And we'll talk of the rules engine and the rules action in a quick bit. But one of these services where you can forward the actions to is AWS Lambda. So moving to Lambda, AWS Lambda lets you run your code without provisioning or managing servers. You pay only for the compute time that you consume, and there is no charge for when your code is not running. With Lambda, you don't have to provision your own instances, and Lambda performs all of the operational and administrative activities on your behalf, such as capacity provisioning, monitoring the fleet health, applying security patches on the underlying compute resources, deploying your code, running a web service front end, monitoring, logging. All of these activities are automatically taken care of. AWS Lambda provides easy scaling and high availability to your code without any additional effort on your part. You can set up your code to automatically trigger from other AWS services or call it directly from any web, mobile, or IoT backend application. AWS Lambda is designed to process events within milliseconds. So Lambda makes it very easy to execute code in response to events, such as changes to Amazon S3 buckets, updates to an Amazon DynamoDB table, custom events generated by your application or devices. For example, you can trigger a Lambda function to automatically create a thumbnail when an image is uploaded to Amazon S3, or notifications are sent from Amazon SNS, or to verify address updates in a DynamoDB table, or even to process clickstream data in a Kinesis stream. Lambda functions can be invoked directly from external sources both synchronously and asynchronously, which makes it easy to build backend services to perform workloads such as image analysis, document transformation, indexing, etc. But most importantly, Lambda functions can also be triggered by AWS IoT events, allowing you to build these serverless backends for your IoT devices. So Lambda allows users to focus on building powerful, dynamic, modular applications in the cloud while not distracting their productivity in the undifferentiated heavy lifting of managing infrastructure. Lambda automatically runs your code on highly available compute infrastructure and performs all the administration of the underlying compute resources. As I said, server and OS maintenance, capacity provisioning, automatic scaling, code and security, patch deployment, monitoring, logging. All you need to do with Lambda is write the code. Lambda supports Node.js, Java, and Python as programming languages. Now our goal is to make Lambda a polyglot platform. That's a platform that supports many languages, so that when you start developing on Lambda, there is no new language which you need to learn. The main benefit of Lambda when building an IoT backend application is this, that there are no servers to provision or manage. You don't need to plan for capacity. You don't need to start scaling your system when there are more devices that connect. You no longer need to go through server patches, upgrades, installation packages, or even be paged for the servers being down. The other benefit is Lambda runs your code only when needed with no unnecessary cost. With Lambda, you don't need to build out and maintain a fleet of servers and then pay for the time that they sit and wait for the jobs to run or your devices to interact with the system. Instead, Lambda charges a low fee per request and for the time that your code runs, making it cost-effective to build solutions that scale from 1 request per month to thousands and thousands of requests per second. The last benefit here is sub-second metering. Now, AWS overall has changed the way traditional IT behavior, where IT admins used to buy hardware servers and pay for everything upfront for a 3 to 5 year commitment, and then they own those hardware servers, and that cycle was much longer for data center leases. AWS changed this to allow customers to pay for infrastructure capacity in chunks of 1 hour, but AWS Lambda takes this to the next level, where you pay in increments of 100 milliseconds. This means that if your API call takes 15.5 seconds to execute, you only pay for 15.7 seconds. These features put together allow you to get an instant 100% utilization on your compute fleet. That's no more paying for idle, no more being under provisioned for peak or being over provisioned for off season. And the combination of these two services working together is very powerful. Now, AWS IoT can act as a front end or the gateway that interfaces with your device using MQTT as a communication protocol and authentication using X.509 certificates. Lambda can act as a compute backend for your service, managing the compute resources for you and executing your custom logic when you need to respond to these device updates. So without managing or setting up any infrastructure or worrying about scaling, you can build your entire application stack in minutes, and the stack will operate at cost efficiently at whatever scale you desire. From here, let's start diving into the working of the AWS IoT service a bit. So the device gateway forms a backbone of communication when the connected devices and cloud capabilities such as the rest of the IoT service need to interact. The device gateway scales automatically with your usage without any operational overhead for you. It supports secure communication with the device gateway, and AWS account level isolation is provided, as well as you have very fine-grained authorization within the AWS account. But we'll talk of this at a bit more depth. I want to talk of the AWS device SDKs. The device SDKs simplify and accelerate the development of code running on these connected devices, such as microcontrollers, sensors, actuators, smart appliances, wearable devices, name any IoT device. First, devices can optimize the memory, power, and network bandwidth consumption by using these device SDKs. At the same time, the device SDK enable highly secure, low latency, low overhead communication with built-in TLS and MQTT support. The SDK also accelerate IoT application development by supporting higher level abstractions, such as synchronizing the state of the device with its shadow on the AWS IoT service, etc. The SDK is also freely available as open source projects. In terms of authentication, control plane HTTPS requests are sent to AWS IoT using AWS IAM, that is SigWe4, or AWS Cognito, both of which support the SigWe4 authentication. If you're using the AWS SDK or the CLI for others, the SigWe4 authentication is taken care of under the hood without you having to intervene. For the data plane operations, HTTPS requests can also be authenticated using X.509 certificates, or MQTT messages to AWS IoT are also authenticated using these certificates. Then we come to the main part of the IoT service of interest here, the rules engine. The IoT rules engine enables continuous processing of inbound data from the devices connected to the AWS IoT service, and you can configure the rules in an intuitive SQL SQL-like syntax to automatically filter and transform inbound data. You can further configure rules to route the data from AWS IoT to several other AWS services, as well as your own third-party services or endpoints. The other thing of interest here is a thing shadow, sometimes referred to as a device shadow, which is a JSON document which is used to store and retrieve current state information for a thing, such as a device, an app, or any other identity. The thing shadow service maintains a thing shadow for each thing that you connect on AWS IoT, or each device that you connect to the service. You can use thing shadows to get and set the state of the service over MQTT or HTTP, etc., regardless of whether the thing is connected to the internet or not. Because the thing shadow sits in the cloud, it's always on, and it will sync with the device whenever it finds internet connectivity. And each thing shadow is uniquely identified by its name. The last component is the AWS device registry. IoT scenarios can range from a small number of mission critical devices to a large fleet of devices distributed to lots of end users. The IoT device registry allows you to organize and track these devices. You can maintain a logical handle in the device registry for each device that you are connecting to the AWS IoT service. Each device in the device registry can be uniquely identified and can have metadata such as model number, support contact, or certificates associated with it. You can search for connected device in the device registry based on the metadata without having to scan all of the devices in the field. And of course, like any other AWS service, you can use the AWS Management Console, the AWS SDKs, the AWS CLI, as well as AWS IoT APIs to access this whole the IoT service. Now let's walk through some of the important components that we touched upon in here. The first one is the rules engine. As we said, rules engine gives your things the ability to interact with AWS services. The rules are analyzed and actions are performed based on the MQTT topic stream. You can use rules to support tasks such as augment a filter data received from the device, or write data received from a device to a DynamoDB table. A rule is basically a SQL statement that specifies the pub sub topics to apply the rule on, the data transformation to perform, and, if any, the condition under which the rule should be executed. The rule is applied on every message that is published on that topic from there on. Rule definitions can use a JSON-based schema. So you can directly edit the JSON using the rules editor or on the management console. Rules include a SQL statement that consists of a select clause and an optional where clause. The select clause allows you to extract one or more JSON objects or attributes from that MQTT message payload. And the where clause allows you to filter those JSON objects or attributes that you just selected. The system supports a lot of inbuilt functions for string manipulation, math operations, crypto support, timestamping, random number generation, etc., which allow complex evaluations of these incoming updates. The rules engine also allows many-to-many operations on your device. So SQL queries can span a whole fleet of devices in a single query, where you need to take action based on multiple inputs rather than just a single input. On the other hand, the pub/sub functionality also allows you to take multiple action based on a single input or a single rule match. The second half of an IoT rule is the actions list that defines the actions to take when the rule is executed or when a match is found. That is, when an incoming message matches the condition specified in your SQL statement. You can define rule actions to write data to a DynamoDB table or a Kinesis stream, or to invoke a Lambda function, or more. Now there are a bunch of actions which are directly supported, including, as we have here, writing to an S3 bucket, writing to a DynamoDB table, publishing messages to SNS, writing to Kinesis or a Firehose stream, republishing the message to another MQTT topic through AWS IoT, or the one of interest to us is invoking a Lambda function. Note that these are the ones which are directly supported, but you can also reach out to external endpoints and take external actions, such as publishing a message to a Slack channel or logging the device state to a Splunk endpoint once you have the data inside the Lambda function. Before we move on, I want to briefly touch on the device shadow. The device shadow enables the cloud and mobile applications to easily interact with these connected devices registered on AWS IoT. The device shadow contains the properties of your connected device, and you can define any set of properties applicable to your use case. For example, if you are trying to build a smart light bulb, you might define on, off, color, and brightness as the properties. The connected device is expected to report the actual values of those properties, which are then stored in the device shadow, and then applications can get or update these properties by a simple REST API. And because this is a cloud-to-cloud communication, it's extremely fast. The IoT service and the AWS IoT SDKs then take care of synchronizing those actual property values. If you update these values from your application, the device will then simply get the update whenever it gets that internet connectivity. So you can have the applications communicate directly to the connected devices using the device gateway or the rules engine. It is possible if you want to go direct to the device communication. However, we recommend using this device registry and device shadows since they offer a richer and more structured development and management experience that lets you focus on the unique value that you create for your customers rather than trying to focus on unreliable networks, the underlying communication, synchronization between the connected devices in the cloud, etc. AWS IoT has also partnered with hardware manufacturers to make these device SDKs available on several IoT, embedded OS, microcontroller type of platforms. We already have partnerships with leading providers such as Intel, Marvell Semiconductor, Broadcom, Texas Instruments, and many others. And we aim to keep this list growing. We have partnered with these vendors to not just for the SDK, but also to build IoT starter kits to get started using AWS IoT. These AWS IoT starter kits enable you to quickly move from idea to prototype. These physical kits are designed to help accelerate the cloud-powered prototype development of these connected devices, which can then securely connect to AWS IoT. The kits include a development microcontroller development boards, sensors and actuators, the AWS device SDK, and a simple getting started guide so that you can easily find the best fit for your product. You can quickly purchase these kits from Amazon.com or these individual device vendor websites. If you already have a hardware board from one of these providers, you can download the SDK and get the samples to get started in minutes. A special case of the IoT starter kit was the AWS IoT button, which we had made available to the AWS IoT mega contest participants at the AWS reInvent 2015. This is the Hello World entry kit to AWS IoT and is based on the Amazon Dash button, which is a stateless Wi-Fi enabled button. The device has a very simple logic embedded into it to store a certificate, connect to Amazon and post a simple message to the host with no additional setup or code required to get started. The device very quickly enables you to learn the rules, shadows, subscription topics, MQTT, etc. for AWS IoT. I have an AWS IoT button with me here today, and our demo is going to start with this workflow. What's going to happen in here in the demo is once I have the IoT button, I will set up the SDK and the private key and certificate on this thing, which will be done as part of the starter kit. These will then go to a rules engine on the AWS IoT service where I create a policy, a rule, and an action. The action is then going to be a Lambda function, which behind the scenes could be any AWS service. But I'm going to pick the Lambda function where I'm going to again show how to build the execution role. And of course, at the end, to make it a complete flow, I'm going to publish to an SNS topic from that Lambda function, which I will subscribe myself to. So let's see how easy it is to configure this infrastructure on the AWS console. This is the only demo we have for today, so I do recommend the audience with any sort of IoT device that they can connect to the cloud to follow along with me and on the AWS console and create a similar setup in your account as a takeaway from this webinar. If you don't have any IoT device, you can follow along for building the Lambda function only and then connect the IoT device whenever you have one. The resources created in this demo will be covered by the free tier of both services, so there is no additional cost for you for clicking along with me. So this is the first step for creating the Lambda function. Once you log into the AWS console and select AWS Lambda, if you click Get Started Now or Create a Lambda function, you will reach the screen. We have a new approach to creating new functions in the Lambda consoles, what we like to call blueprints. A blueprint is a set of configurations and sample code to quickly get you started for integrating with a specific trigger. Here I'm going to bypass this, however, by clicking skip at the bottom of the screen and start building my own function. Now for creating the function, Lambda gives you three options. The first is to edit the code in line, which gives you this WYSIWYG type editor where you can directly start typing your code. You can also upload your code along with any additional dependencies or binaries in a zip file directly to the Lambda console. Alternatively, you can upload the zip file to S3 and then provide the S3 object details as the source of your Lambda function, which allows you to integrate custom deployment tools directly with your Lambda functions. As you can see here, all the code does is log these incoming events. It creates an object to publish to SNS, and then it calls SNS.publish, where I'm going to post this message to a pre-configured topic which I already have created. A few additional configurations are needed for you in this step here. The first configuration on the Lambda console is to select the execution role for the Lambda function. This permission is to allow Lambda to take action on your behalf by interacting with other AWS services. For example, this Lambda function we wrote needs to read and write to put data to the CloudWatch logs as well as publish to an SNS topic. The Lambda console provides easy templates for creating these execution roles, or you can select existing roles if you have one. I'll come back to this role creation in a second. You need to select the memory that you want to allocate to your function and the timeout that you want to set. Now we leave these two values to default right now, and we'll fine tune these later if needed. So now let's look at role creation a bit more. Here, if we select create a new execution role, it automatically directs us to the IAM console on AWS with a pre-populated policy document. You can change the role name here on the IAM console, or can expand or edit the policy to add more options. Let's take a quick look at the policy document. As you can see, this policy allows your Lambda function to do two things here. It allows Lambda function to make any changes to CloudWatch logs, and the other one allows it to interact with SNS. When you click allow on the IAM console page, it will automatically take you back to the Lambda console where this policy was created, and it will attach to the Lambda function that you are creating. This list step is only for verification of all the configurations you have set. If everything looks okay, you can create the function if you're done with setting up the Lambda function. And that's pretty much it. You can see that we have successfully created the Lambda function. From here, let's try to test the Lambda function to make sure that everything works as expected. You can click on Actions on the top of the screen and configure a test event object. You can change the object as needed. You can select a few of the samples that we have from the dropdown, or you can create your own object type. Note here that I have only one field in this called payload. If your IoT event that your schema has your device has a different schema that you will be using, then you will need to change this object and the code accordingly for the Lambda function too. So once you have changed this to set what you have in the code, if you hit save and test, what will happen is that it will execute this Lambda function once directly straight from the console, so you can get an inline debugging experience. As you can see, this Lambda function was a success. Upon this, you will also see that the logs were published. What we had was a incoming buffer as well as the test message, which we see has been now processed by Lambda, has been appended to it. Also, what would have happened here is that this message would have been published to SNS. As you can see, it shows great success JSON, and it shows the SNS topic which was published. I had already created SNS topic in the backend and have subscribed my own email to this topic. So if you move over to my inbox, which was subscribed to this topic, you will see that I got this email that says test message processed by Lambda. So that's the AWS Lambda side of the configuration. Now let's move over to the IoT side of the configuration. Whenever you purchase the SDK or the development kit from any of the vendors, or you have the AWS IoT button, you will have this activation screen as part of the kit, where once you enter the specific identifier of the device, you will be given the option of activating the device or the kit. Activation normally means three things. First is that you create that thing on AWS which effectively creates a device shadow and a registry update. Second is that you create a certificate for that device. And the third is to create a policy on AWS IoT that allows the device to publish to AWS IoT from there. From there, what I'm going to do is configure a custom rule. I can do this straight on the activation screen if that's what my device SDK enables, or you can go to the AWS IoT console and create a rule. Here you can see I'm going to create a rule called SNS to Lambda, which creates the SQL query select star from IoT button. And the action that I'm going to take at the bottom is to publish to a Lambda function. And here I pick the Lambda function that we just created. So what that Lambda function is going to do is going to log it to CloudWatch logs and then publish it to SNS. So once you select create over here, if you go to the AWS IoT console, you will see all of these show up. You will see the policy that you created, the button or the shadow, the certificate, as well as the rule that we just created. And you can click on any of these to see the status of what the status of the device is, when it was last sync, what the shadow update is, and what the delta is between the actual and the expected. So with this, we're ready to go. When I click on my IoT button over here, which I'm afraid I can't show you, if I click on that button, it's going to publish a message via MQTT to the AWS IoT service. The device gateway will receive that. It will in turn forward it to the rules engine. Because the rules engine is set to select star, it will trigger the rule, which will invoke a Lambda function. That Lambda function is pre-configured to write to logs and publish to SNS, and I have subscribed myself to SNS. So when I click on that button, what's going to happen is, as you see, I'm going to get the second email, and it's going to send the entire payload from that device, which includes the device serial number, the battery voltage, what type of click I did, and of course, because it's processed by Lambda, it's going to append that at the end. Now, while this was a simple demo where I get an email notification on clicking a button, which by itself is not too attractive, the power of this is that the logic is now totally configurable via the AWS IoT rule, and the action is completely configurable via the Lambda function. So you can build very powerful applications using this combination. For example, every time my smart weather sensor indicates a temperature of 60 degrees or lower, go and turn on the heater in my house. Or if my factory liquid flow regulators indicate a buildup in pressure, then automatically shut down those components and then page the on-call supervisor. The use cases for smart IoT devices where the smartness lies in the cloud and is configurable and is software which you are writing in the form of a Lambda function, the use cases for these are limitless. So before I end, I'd like to show an alternate configuration of how you could build a production grade IoT backend. And we have this reference architecture on our website today, which demonstrates how to use Lambda in conjunction with a DIY setup to replicate the functionality of the AWS IoT. This includes Amazon Kinesis, Amazon DynamoDB, Amazon S3, Amazon CloudWatch, etc. to build a serverless system for ingesting and processing sensor data. This repository, which I have listed here, contains sample code for all the Lambda functions as well as AWS CloudFormation templates for creating the functions and all of these related resources. There's also a simple web page that you can run locally if you don't have an actual device to test, which will publish sample events and query the data from DynamoDB. Let's also look at the reference architecture diagram and break down each of these components to give an idea of what the setup is. You can access this entire reference architecture on the link which I have provided here. However, the box label 1 at the bottom is Amazon Kinesis. This is going to act as the ingestion for the events. Devices would send events with data to Amazon Kinesis, which provides a large-scale durable storage for these events for up to 7 days, and also allows multiple Lambda functions to process these events. Number two to its right next to it is the first Lambda function. This function processes the incoming events and stores the event data in a table in DynamoDB for low latency access. It also sends values to CloudWatch for simple monitoring and to generate aggregate metrics. Number 3 on the right is the second Lambda function, which processes the same events as above, but then aggregates and stores all of these events coming in to Amazon S3, that's the box number 5 on the further right, for cost-effective long-term durable archival. Storing data in S3 also makes it easily accessible for analytics processing with Amazon Elastic MapReduce or EMR and Amazon Redshift, which are blocks 6 at the top. Event data no longer needed in Amazon S3 is automatically migrated to Amazon Glacier or deleted after a certain retention period using the S3 object lifecycle management. Now blocks 6 also represent the analytics portion of the setup, where Amazon EMR runs jobs that read and write data directly to DynamoDB and to S3 to analyze the data, generate aggregates, create billing reports from the large set of events that is gathered from the device fleet. The event data from S3 is also loaded into Amazon Redshift, which allows interactive exploration of the analysis using the standard SQL queries, where you can store lots of information at a very cost-effective and highly performance way. The setup here includes a bonus box number 4, which is a third Lambda function that provides a synchronous interface that devices can directly call to for retrieving data from DynamoDB. This can, for instance, be used to retrieve configuration information or historical event data if the devices need to pull that information from the system. Now, a large portion of this setup, excluding the analytics portion on block 6, and the Lambda functions can be replaced directly with AWS IoT. And we invite all of you to give it a try and build similar reference architectures and let us know how it goes. So in summary, we have 3 next steps for you from here. We invite everybody to connect any IoT device that you have to the AWS IoT service. And if you don't, then purchase one of the AWS IoT hardware starter kits to get started. Now, these are available all on Amazon.com or on the device on the website of our hardware partners. With just a few clicks in the management console, you can create a device policy, you can create a rule, and you can create an action that allows you to securely and easily connect your device to the cloud and then access data, business logic, functionality, etc. from the backend services. The second one here, which I have labeled all of them as one, is to create and test your first Lambda function. With Lambda, there are no new languages, tools, or frameworks to learn. Now, you can use any third-party libraries, you can build native libraries, You build code the way you are used to building code in your own IDEs. All you have to do is upload the code to Lambda and let Lambda take care of the rest. And every month, the first 1 million invokes are on us. So there's a pretty generous free tier, and we invite you to take part in that. And the third one is to select Lambda as the rule action for your AWS IoT device, is to connect these two services together. And you can use the sample codes and setup instructions to quickly create your first IoT backend using AWS IoT and AWS Lambda. And we absolutely invite you to give it a try and let us know how you find the service. So with that, we thank you very much. Now if you have any further questions, we might not be able to address them directly in the webinar, but you can go to any of these links and post the questions which weren't answered.